Yeah, hello and welcome back to our string theory course. Before I continue with the lectures, I would like to remind you that the example sheet number 2 is out for you to work through, and I'll probably will release solutions about next week. So last time, towards the end of the lecture, we started to go over conformal field theory the second time, now from a top-down perspective. And I started with a few remarks about conformal symmetry in general dimensions. We saw that conformal transformations in particular include the Poincaré transformations, and that there's two ways of extending this. The first way is that we add scale transformations or dilatations. Then the resulting group still acts by affine transformations, meaning we have linear transformations acting by matrices and translations. However, the full conformal group also includes so-called special conformal transformations, which don't act affinely. And then if we want to have a proper group action over all of space-time or space, then we need to add points at infinity and consider the so-called conformal compactification. I gave you a few general remarks about scale and conformal invariance and how they are related. I think I don't want to repeat this now, but mention some examples which are good to know with regard to the point that is made here as the last bullet point, namely that classical scale invariance is not only can be broken, but it actually is generically broken by quantum effects. Good example is four-dimensional Young-Mills gauge series with massless matter, say QCD with quarks, but quarks which are strictly massless. As a classical series, this is conformally invariant. But to define the quantum theory, we need to renormalize it. And the renormalization procedure introduces a scale which survives into the fundamentally defined quantum theory once we remove the cutoff. And the technical way this manifests itself is that in the quantum theory, the coupling constants become so-called running couplings, which means they are dependent on the energy scale. And this energy dependence of couplings is measured by the so-called beta functions. So in order to have scale and conformal symmetry in a quantum field theory, one needs that these beta functions vanish identically, which generically they don't, even if the theory is classically conformally invariant. However, there are examples where we believe that conformal symmetry is exact, and these are a series with additional symmetry, notably extended supersymmetry, so having a certain number n of supercharges, which are symmetries of the theory. And the prime example is the n equals to 4 super Young-Mills theory in 4 dimensions. That is the maximal amount of supersymmetry that you can have in a quantum field theory without coupling it to gravity. And the n equals to 4 super Young-Mills theory has vanishing beta function, is believed to be a sound example of a conformal field theory. You can also get conformal invariance in n equals to 2 super Young-Mills, where you have less supersymmetry, if you fine-tune the meta content in such a way that the beta function vanishes. And some people are even trying to do the same for n equals 1 and maybe n equals to 0 theories, but there it becomes more complicated because with less symmetry, you have more allowed quantum corrections that you need somehow to cancel. Now back to 4 dimensions. In Lorentz signature, the conformal group that we predict from our general analysis in generic dimensions SO2, that group is a bit special because it is a product of two groups, which we can write as SO2, or SL2, R, and this acts then on the conformal compactification of Minkowski space, which amounts to adding one point at spatial infinity. Euclidean signature, the conformal group is, what we predict is SO1,3, which looks like the Lorentz group in 4 dimensions. But a better way of thinking about this is the group SL2C of determinant 1 complex 2x2 matrices. We have already seen how this acts on the complex plane by fractional linear transformations, and this becomes a well-defined transformation if we include a point at infinity. However, if you recall the formula how this operates, Z goes to A, Z plus B over CZ plus D, where A, B, C, D is a matrix. Now you see, if you take this matrix to be the identity or minus the identity, it will have the same effect on Z. And that's why the group which actually acts on the complex plane or on its compactification is SL2C with a plus and minus identity identified. This is the projective version of the special linear group, and this is also called the Möbius group. The Möbius group. And it's a conformal compactification of the complex plane is simply the Riemann sphere. However, in 2 dimensions, the real important thing is that we have a Lie algebra of infinitesimal conformal transformations, which is infinite dimension. And despite that these transformations do not exponentiate to be well-defined finite transformations, they still impose very strong constraints on conformal field theory. Technically, these are then Ward identities, conformal Ward identities, which means that the correlation functions of the theory have to satisfy certain differential equations. And these are very strong constraints, which for a subset of theories means that we can solve them exactly. We will come to this back a bit later. Okay, here's some general blah about what is special about conformal field theories in 2 dimensions. So one of the strengths of the formalism that we are using is that we work with OPEs. And if we do this in a general setup, we don't need to require that the fields, the theory is built of its free fields. We don't need to know an XZ action principle or even whether it exists. What we're just doing is exploiting the infinite dimensional conformal symmetry algebra. And that, roughly speaking, makes solving the theory to understanding the representation theory of the relevant algebra, which is the so-called Virasoro algebra, which we will see in generality arising in a few slides. So we now discuss conformal field theory from this general perspective and in a top-down style. For string theory, this is useful. We will use, of course, some elements to define the quantum theory in the next part of the lectures, but these methods are in particular important when you study strings on general curved spacetimes, which we might mention towards the end of the course. So to start, we define what a primary field is, primary field of weight h and h bar. And that is simply a field which transforms as a cotensor of type h bar under conformal transformations. And it is this formula which then states what this means. From this formula, we can, of course, solve for phi prime, and then we have the usual transformation behavior for a cotensor, except the somewhat unusual thing is that these tensors and cotensors only have a single component. Still, it's important to keep track of the weight, because this decides how these functions, which are technically not functions but components of a tensor, do transform. Sometimes one reminds oneself of this information about the weights by writing as many z's and z bars as indices as h and h bar has as a value. So that reminds us that these are tensor components, but the indices Z and Z bar only take a single value, and these tensors have only a single component. By the way, the reason we here take cotensor instead of a contravariant tensor is that we will later see that in a unitary conformal field theory, these weights have to be non-negative. So with this definition, H and H bar will always be positive or zero, but never negative. Often we work with infinitesimal conformal transformations, so let's spell out also in more detail. So the infinitesimal variation is a difference between phi prime and phi, both taken as the same coordinate value. If we evaluate this, then by definition it is minus the so-called Lie derivative. And if you work it out from formula 2, then you should find this formula here. And that's also a very central and important formula. As remarked here, the relation between Lie derivative and infinitesimal variations of tensor fields is general, but the point here in deriving formula 2 is that we want to have the specific expression for the conformal transformation of the infinitesimal transformation of a conformal primary with given weights H and H bar. Some terminology. If H bar is 0, we call the field holomorphic. If H is 0, we call it anti-holomorphic. And often we will just consider one sector, by default the holomorphic sector. Now, if a field is holomorphic, then the coefficient function is not required to be a holomorphic function. It could be just a real or real analytic function, but it need not be holomorphic, or real differentiable function, but does not need to be holomorphic. Now, holomorphicity, which we can express as depending only on Z bar and not on Z, is an extra condition, which corresponds in Minkowski's signature to be purely left-moving, and such fields are called chiral. And very often we will be working with chiral fields. Two of the conformal transformations are particularly important and give rise to parameters that we associate with a field. Firstly, dilatations or scale transformations. The behavior under a scale transformation defines the scaling dimension or dimension of phi, which is H plus H bar. And note that with this minus sign here, the coordinates themselves have weight -1. But this here is defined in the right way for us. That these weights H and H bar are positive, as I explained before. And the quantity associated with rotations is a difference, and it's called the conformal spin. This also makes sense because there's a rotation subalgebra or rotation subgroup in our conformal algebra or group, and conventionally such a quantity is called the spin. Of course, if we continue the theory back to Lorentz signature, then it will be one time and one space dimension, and there will be no real rotations, only Lorentz boosts, which are then labeled by the so-called conformal spin. Right. Mode expansion in general. So for a chiral field of weight H, this is a mode expansion that we write, and note that we have defined in the mode expansion here this extra factor H, or this extra term H. This H is implied by the conformal transformation that we made from the cylinder to the complex plane. If you go through the details, then this creates this extra factor Z to the -H in the mode expansion. So again, this is necessary so that we are consistent with how we have set up mode expansions in Minkowski's signature originally. We then can use the residue theorem to project out the modes. And our next task is to define Hermitian conjugation. And again, what is important is we want to keep consistency with the Minkowski space version. Now, what is crucial in the Minkowski space version is this relation here between the modes. Namely, if I take the nth mode of the field phi and then take the Hermitian conjugate, then this is the -nth node of the Hermitian conjugate field. And this is what I should keep. And this leads to this, at first, slightly counterintuitive definition how phi dagger is related to phi of z Hermitian conjugated. But it is, I claim, needed to preserve this relation, and I will explain this on the next slide. Now, also to emphasize why this is important that we keep this relation, in particular, if we have this relation here, we can use it to impose a reality condition and then define what in Minkowski signature is called a real scalar field and what we might here call a Hermitian scalar field, namely a field where the modes of the fields phi dagger and phi are determined by each other. So now let's explain in the next two slides why this slightly funny looking formula is needed for Hermitian conjugation in Euclidean signature. And let's first remind ourselves how it works in Minkowski signature on the Minkowski cylinder. We have a mode expansion for phi, which is defined as such. And I can take the Hermitian conjugate. This puts me a dagger here and flips the sign here. And then I define the field phi dagger again by its mode expansion, and I call its modes phi dagger n. Now here, it is manifest that imposing that I want that phi dagger of sigma is phi sigma dagger, then it gives me this relation between the modes, and this I can use to impose this reality condition. Now let's look how this works in Euclidean signature. So first of all, we have mode expansion of a field phi as defined before, and if I take the Hermitian conjugate, then the operator is Hermitian conjugate and I have a complex conjugation acting on z bar. We already observed that we have extra factors z minus h and z bar minus h, which come from the conformal transformation that we have made to the plane, but also observe that complex conjugation acts slightly differently because we have analytically continuous sigma. Now, if we then want to preserve this relation, where phi dagger is again defined by having a mode expansion as a weight h conformal primary, then you can readily check that it is this relation that we need to have. Okay, so much about Hermitian conjugation. Briefly about radial ordering. So only radially ordered product of bosonic operators are defined, and this is our radial ordering prescription here. Since only radial ordered products are defined, the symbol R will usually be omitted. And then if we consider quantities defined at equal time, we have to do this by a limiting procedure. And in particular, we have already seen how we concretely evaluate commutators between modes by choice of integration constant. For fermion fields, which we will not discuss in this course, it is the same story with anti-commutators instead of commutators. Now the energy momentum tensor. Before we knew, in our example of a free field here, we knew, of course, what the energy momentum tensor was. It was dx, that was a tz z component. But in general, we don't know how the energy momentum tensor is expressed concretely in terms of fields. So we want to have some general characterization of what an energy momentum tensor in a conformal field theory should satisfy. And what we impose is the following. It should be traceless, which in complex coordinate means no mixed components. This implies conformal invariance, and should be conserved, which we can write out, and which that means that among the remaining components, that TZZ and TZ bar, Z bar are chiral fields, meaning they only depend on Z and Z bar, respectively. And now we can turn to a discussion of infinitesimal conformal transformations resulting from this. General rule is if we have a conserved current, which in complex coordinate means this, and we have here even chiral conserved currents where this here is even separately conserved, then we get a conserved charge by integrating over space, which for us means integrating around the origin of the complex plane. And then the conserved charge has the important property that it generates in an infinitesimal symmetry transformation by taking the commutator between field and generator with the usual minus sign, because we do everything from the passive point of view. So with the energy momentum tensor, it's of course, and we have seen this in Minkowski signature before, that the conserved chiral current is not the energy momentum tensor itself, but the energy momentum tensor contracted with an arbitrary chiral vector field. And this is the reason why we get infinitely many conserved chiral and antichiral currents, corresponding to infinitesimal conformal transformations. So in our case, the conserved charge is this product or contraction between an arbitrary holomorphic or allomorphic and chiral vector field and the energy momentum tensor integrated around the origin. Therefore, the infinitesimal conformal transformation of a chiral primary is given by minus commutator t with phi, which we can write out in this way as a contour integral, where the commutators implement by our choice of contour. And this is something that I leave to you to verify explicitly. We can show that the transformation law, which we have derived for a conformal field theory, for a conformal primary of weight h, is precisely equivalent to this operator product expansion with t and phi. So if the operator product expansion t phi takes the form phi, then the infinitesimal transformation law 2 follows, and the other way around. So this is a general structure of the OPE T phi for any chiral primary of weight h. And we say it has a second order pole as the leading term in the singular part. The phi is reproduced with the weight h as coefficient. And then there's a subleading term where we have the derivative of the scalar field. Now with this insight, we can indeed confirm something that I claimed in the previous part, namely that the derivative dx of a free scalar has weight 1,0, whereas its exponential e to the ikx normal ordered has weights 1/8 k squared, 1/8 k squared. The infinitesimal transformations must form a Lie algebra. In particular, means these transformations must close among themselves. And with some effort, one can show that this fixes the form of the OPE of T with itself. And this is given in formula 5. When we computed T of Z with T of V for the free scalar field, we indeed found this form with a specific value for the coefficient C. But now the claim is, if we just impose that T creates infinitesimal conformal transformations of chiral primaries, and the transformations close into a Lie algebra, that this is the most general OPE that we can have with an undetermined coefficient C. And our first example already shows that this coefficient is in general there. Now, it's a bit complicated, or takes a bit effort to work this out in general, but I can give you another quicker argument why this is the most general singular part of the OPE that we can have for the energy momentum tensor with itself. Namely, we can use that if this relation is consistent with conformal symmetries, in particular consistent with dilatations, and therefore the scaling weights of the fields must balance. Now the scaling weight of T itself is 2. Let me make this flat so I can write a bit better here. So T itself has a weight 2, and 2 plus 2 is of course 4. And we can then check, so the terms that we would also have in the OPE for conformal primary are, for example, this term here. T itself has weight 2. For coordinates, we saw that they have weight -1, but here the coordinates appear squared in the denominator, so this is 2 plus 2. Coordinates have weight -1, therefore a derivative has weight 1, so this here is 3 plus 1. And then the only other possible term which is possible is a fourth order pole, because this has weight 4 on the nose. And the coefficient, numerical coefficient, is not determined by anything. Now, maybe we should also convince ourselves that we know in generality that the weight of the energy momentum tensor is really 2. So how do we know this? Maybe for this I need a bit more space. So let me take a blank sheet. Oh, there's not a blank sheet here. Nope. Okay, maybe I use this. Nevertheless, making some space first. So in our previous example, T of Z was proportional to dZx, and x had a weight 0, and then if you take a derivative, we get 1 plus 1 is equal to 2. Now, how can we see that this must be true in general? Well, in general, I can define the energy momentum tensor as a response of the action when I deform the metric on my worksheet slightly. So that is this formula here, which says the S is up to a numerical factor integral d2 sigma, or d2z. If you prefer, you can also write d2z. But it's important we do this on a general curved worksheet, and then variation of metric contracted with the energy momentum tensor, and we now talk about the energy momentum tensor with lower indices. Therefore, it is the variation of the inverse metric here. Now, the theory is conformal, therefore the action and its variation must have weight 0. This here, product of all coordinate differentials multiplied by square root determinant of the metric, this is the invariant measure. So this, by construction, has weight 0. The metric H alpha beta with lower indices has weight 2, but this means that the inverse metric has weight -2. And since the energy momentum tensor is whatever is produced here, if I make a variation of the metric, this has weight 2. So it's quite clear that we could use this, that our energy momentum tensor must have weight 2. And where are we? Are we here? Yeah, here we are. So, and this gives us a quick argument why this is the most general OPE that we can have. So, if we would just have this here, T would be a conformal primary of weight 2. We still say it has weight 2, but it's not a conformal primary because of this extra term. So let's explore the consequences. So the infinitesimal conformal transformation law is not quite tensorial because it has this extra term, which goes with the undetermined coefficient C, which for free scalar field is C equals to 1. And since it goes with the third derivative of the component of our generating vector field, there are some transformations for which this term is absent, and the transformation behavior is tensorial. And this is precisely the subalgebra SO2C, which we have already encountered several times. You can, with some effort, also derive the finite transformation law. So for finite transformation, this here would be for something which carries weight 2. Then the extra term is something which looks very complicated, but luckily it is known from the theory of complex functions. It's called the Schwarzian derivative, and it plays a big role in slightly advanced chapters on functions of complex functions, modular forms, automorphic functions on the Riemann sphere, and so on. In particular, it's a standard fact about the Schwarzian that it vanishes exactly for Möbius transformations, which we could also have predicted from the infinitesimal version. So the upshot is that T of Z is not a tensor under the full conformal Lie algebra, but it's still a tensor under the Möbius subalgebra, which also exponentiates into the Möbius group. Some more definitions are motivated by this. So we said primary fields are fields which are tensors under all conformal transformations. Whatever is not a primary will be called a secondary. And we will see later that such secondary fields truly appear in a systematic way as so-called descendants from primary fields. Examples that we have already seen is, of course, the energy momentum tensor itself, which we will see that descends from the unit operator. But we have also seen that higher derivatives of a scalar field were needed in our particular example from the previous part. And these are then descendants from the first derivative, which is a conformal primary. And we will introduce a special name for secondaries, which are at least tensors under the Möbius group, and they are called quasi-primaries. And the most important example is, of course, the energy momentum tensor. Now that we have the OPE of T with itself, we can convert it into a Lie algebra, into commutation relation between its Laurent modes by our usual use of the residue theorem. And the algebra that we get is given in Formula 7. And this is the celebrated Virasoro algebra in full generality. If it was just for the first term, this would be the Witt algebra describing infinitesimal conformal transformations. But we have a modification, a term which is central because it's proportional to the unit operator, which centrally extends, as one says, the Witt algebra into the Virasoro algebra. In a given conformal field theory, C is always a fixed multiple of the unit, and therefore one often talks about C as if it was a number and calls it a central charge. So one would say the theory of a free mass scalar field has central charge C equals to 1. And to put it in general context, this illustrates the two-dimensional CFTs. In two-dimensional CFTs, the conformal symmetry has an anomaly, which means that the classical symmetry algebra is extended in a non-trivial fashion. This is not an inconsistency, but just a feature. And it is very critical for having something non-trivial at all, because we will see later that if we want to have non-trivial unitary conformal field theories, C equals to 0 has to be discarded. So C equals to 0 would never give us a non-trivial unitary CFT, whereas with positive values of C, we can have non-trivial unitary conformal field theories. So the anomaly is a price for having something that we can call a conformal field theory at all. Here's some more context on the conformal anomaly. Another way of characterizing the conformal anomaly is to look at the expectation value of the trace of the energy momentum tensor. And the way, and more precisely, you do this, you evaluate this vacuum expectation value on a worldsheet where you have switched on a non-trivial metric. So what in a sense you do is you have a theory which you think is conformal, but then you deform the worldsheet theory by deforming the metric, which effectively introduces a scale, namely the curvature radius, say, of your metric. Now, for a two-dimensional metric, the curvature properties are characterized by the curvature radii. If you draw circles through a given point and measure their radius. And this measures the anomaly. And the general formula for the anomaly is that the trace anomaly of the energy momentum tensor is proportional to the Ricci scalar of the metrics that you put on your worldsheet. And this shows you how the theory responds if you make the worldsheet curved, and it tells you to which extent then conformal invariance is violated by this. Okay, but this was a side remark. Now, back on track, conformal transformations of chiral primaries. We had an OPE. Now, it was the OPE T of Z of W is H pi of V Z minus W squared plus a subleading term. And from this, we can now also derive commutation relations from modes. And I've given you two versions. In the first version, I have ln acting on the full field phi of z. And then in the second step, I also project out the modes of phi and give you the commutator ln phi. And both formulas are useful. What is currently nice for us is that the formula which I've encircled shows us that the operator ln corresponds to a conformal transformation with a generating vector field, which is, generates a transformation with z to the n plus 1. So we know precisely which of these mode operator corresponds to which basic conformal transformation in the geometric picture. And then the LNs implement these geometric transformations as transformations on the fields. Let's next revisit the state operator corresponds. And again, we now need to formulate this generally without reference to a specific theory. So the Hilbert space is generated from a ground state 0, and in particular the ket state we might call the in vacuum, and we generate a Hilbert space associated to this reference ground state by taking operators evaluated at z equals to 0. This is something that we have seen concretely in the previous part. And similarly, we can do this with the out vacuum by inserting fields at the position z equals to infinity, meaning on the north pole on the Riemann sphere. Now, what should we require for the behavior of this ground state and behavior of the energy momentum tensor if we insert the energy momentum tensor at the origin? Certainly, the state which is generated if we apply the energy momentum tensor at the origin should have finite norm. So it should be regular. And that means if I look at the expansion, that all the terms which come with negative powers with z should annihilate the ground state, because these are the terms which will blow up. And that tells me that the ln's with n larger than -2 must annihilate the ground state. And very nicely, these are exactly those conformal transformations which we know are regular at z equals to 0 if we consider them as geometric actions on the coordinates. So it fits quite well together. Regularity conditions that we impose in terms of geometric transformations on the worldsheet and how these transformations are then implemented on the operators. We can repeat this for z goes to infinity. And what we find that in this case, ln acts as annihilator to the left if n is smaller than 2. Okay, you have to use what you know about Hermitian conjugation, and when you take the limit z equals z to infinity and do everything formally correct, you should make a coordinate transformation and introduce a new coordinate which is well defined in this limit, etc., etc. I leave it to you as an exercise to spell out the details. But what you then again find is that the ln's which are regular at infinity are also correspond to those transformations which geometrically act regularly at infinity. And if you combine both conditions that we have imposed, then we find in particular that the operators L-1, L0, and L1 annihilate both the in vacuum and the out vacuum. And since these generates the Möbius group, this is then called the SL to C vacuum of conformal field theory. So the standard vacuum of conformal field theory is the SLC vacuum, which has a property that is annihilated both to the left and to the right by the Möbius group. Yeah, we also need to specify what is a reasonable behavior if we apply chiral primaries on this SL to C vacuum. Same logic, if we insert a chiral primary at the origin, then the state should have finite norm. And this fixes that phi n with n larger than -1 annihilates to the right, and phi n with n smaller than h annihilates to the left. Now, you might observe that if H was allowed to be negative, then there would be modes which neither annihilate the in nor the out vacuum. So these are states which are not clearly identified as creation or annihilation operators. I will ignore this here because I will show you that in a unitary CFT, one must have that H is non-negative. However, there are situations where one has to deal with non-unitary CFTs, and then one has to discuss what to do with these fields. I won't do this in these lectures, but it is a relevant problem, and there is answers about how to deal with these fields. Where are the applications where these fields are relevant? Now, there are applications in condensed matter and statistical physics where you consider, or more generally, whenever you consider an open system where information can flow in and out, then the theory just describing the open system need not be unitary. And for these situations, you need also to deal with these non-unitary CFTs. In string theory, the non-unitary CFT appears as an auxiliary sector associated with the so-called Fadeev-Popov ghost. So if you have seen the for example, the functional integral approach to non-abelian gauge theories, and you are familiar that there's some kind of technical device, some kind of auxiliary fields called the Fadeev-Popov ghost that one has to consider. And at some level, it also becomes necessary to talk about these Fadeev-Popov ghost fields in string theory. And then this is a non-unitary CFT, which has precisely these properties here. Some of the books that I've recommended for reading for this course deal with this. So you can read up on this, but I won't have time to cover this here. So rather, I note that now in-states are defined by inserting chiral primaries at the origin, and this corresponds to applying a particular mode from the mode expansion at the origin, and yeah, and so good. Now let us just note that the state operator correspondent works out consistently in the following sense. The field phi at the position 0 is related to the field at position phi of z by action of the translation operator, and on the complex plane, L-1 is the translation operator. So this is how we translate a field from position 0 to z. But this is equivalent to saying that if I apply to our ground state a field which is evaluated at z rather than at 0, then I get the state phi, which is phi of 0 on the ground state, but now translated to the position z. So that confirms something that I've already told you informally a couple of times. The operator formalism gives us the flexibility to create any state at any given point on the worldsheet. And while I'm usually talking about the cat states, the discussion for bra states is fixed by taking the permission conjugate. Now, let's talk a bit about the representation theory of the Virasoro algebra and how it helps us to master conformal field theories. For this, I motivate now the definition of a so-called highest weight state. We start with the observation that if we use a primary field to create a state, then this state is an eigenstate of L0. The eigenvalue is precisely the weight, and the positive Ln's annihilates the state. Therefore, we can only create new states by applying the L-n's, where n is a positive. And this turns out to give us, for every such state associated with a primary, an infinite tower of further states in our Hilbert space. And one immediate observation is that if we proceed to create states by application of L-n, then the states that we create are still eigenstates of L0, with the eigenstate shifted precisely by the mode number of the operator that we used in order to create the state. So we get a systematic tower, and what happens is that the L0 eigenvalue increases. In terms of physics, it means that if we apply a primary field, we create the ground state of a certain sector, and then by applying the operators L minus n, we get excitations which have higher energy. Unfortunately, the terminology in mathematics is the other way around. In most of the mathematics literature, one then says that what physicists would call the vacuum or minimal energy state is called the highest weight state, and then they regard the operators which create this tower of infinitely many states as lowering rather than raising operators. But this is just a conventional minus sign in terminology, which need not bother us, hopefully. Okay, this is highest weight states. Again, we need some words to refer to things. So states obtained from a highest weight state by applying these operators L minus n are then called the descendants. And if you have a conformal field here with a certain charge C, then starting with a conformal primary of weight h, and applying these operators L minus n, we create a subspace of our Hilbert space, V of C and H, which is a representation space for the Virasoro algebra, and which is called the Werner module of this highest weight state. Module is just another word here for representation space. We know what the basis is for this Werner module. Namely, it is obtained by applying all possible raising operators L minus K1 and so on. And it's clear that all these states are eigenstates. Applying these operators will always shift H by a certain value. And this value, which is a difference in the L0 eigenvalue between the ground state and the excited state, is called the level of the state. So it's very convenient. States are organized by levels. And okay, in terms of the string mass spectrum, we will see later that these are the values that the mass squared takes. So essentially the energy of the string states take. If we choose a basis of highest weight states which are orthogonal to each other, then states in different Werner modules will be orthogonal to each other. And within each Werner module, I claim that states which are at different level are automatically orthogonal. This is something that you might want to check. And then within a Werner module at the same level, states are not automatically orthogonal, but you can always select an orthogonal basis using the Gram-Schmidt algorithm, which you might remember from linear algebra. If you have some set of vectors with given scalar products, then you can always construct a new set where the states are unit lengths and orthogonal to each other. Now with descendant states come descendant fields by the state operator correspondence. So there is some notation for this, which is pretty obvious. The descendant states corresponding to the application of one single L creation operators appear immediately in the OPE between T and phi. And by looking, and with OPE here, we now consider the full OPE, including regular terms. And by projecting out these modes, that we see that these are essentially derivatives of the field phi. So all derivatives of a conformal primary appear as descendants. And then there are also descendants which are related to applying two or more of the L operators. And for this, I have to iterate the construction and take OPEs between T and the descendants that I got before, etc., etc. And the whole bunch of fields that I get in this way is called a conformal field theory, and sometimes denoted by this symbol here. Okay, as a little check that you understand the definition and are able to apply it formally correctly, you can convince yourself that the energy momentum tensor is the level 2 descendant of the identity operator and therefore belongs to the conformal family of the identity. Little self-test. Okay, good. I think my alarm will shortly go on and remind me that I have to wrap up the lecture. So let me already give you a preview of where we will continue. with the CFT part next time, and I'm pretty sure we will also finish this. So what I would like to give you next is a general discussion of operator products, product expansions of their structure, and give some indication how this leads to a partial classification of conformal field theories. And after that, I will talk about partition functions in the context of conformal field theories, but also already with an outlook on how this relates to partition functions in string theory. And these partition functions are very handy because these are functions which encode the whole spectrum in conformal field theory, the operator spectrum in string theory, the particle spectrum of the theory in a single function, and you can read off certain rather deep properties like the so-called modular invariance out of these functions. Okay, good. My alarm has got off, so I should now end the lecture here. Hope everything was clear. If not, please let me know, and otherwise I'll hang out for a bit until everybody has left. Otherwise, I wish you a good day, have a good week, and see you all next time, next week, same time, same place. Bye now.